Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to describe evaluating a polynomial at a point and Horner's rule. So in this topic, we will describe the representation of polynomials. We will discuss the idea of evaluating polynomials, and then we will look at a sequence of more efficient implementations of doing so. Now, we are going to use C++, and then at the end of this talk, we will describe the evaluation of polynomials in Matlab. Now, the way we are going to represent polynomials in C++ is the same way that we represent polynomials when we show the coefficients. So the index of the coefficient equals the power of the term. So the array entry AK is going to be the coefficient of x to the k. So, for example, here we have a polynomial of degree 2 with coefficients 2, 3, and 1, 2 being the constant coefficient, 3 being the coefficient of x, and 1 being the coefficient of x squared. Now, in Matlab, however, all polynomials are represented with vectors. So an n-dimensional vector in Matlab represents a polynomial of degree n minus 1. Now, if P is a vector and it's representing an n-dimensional vector, then pk is the coefficient of x to the n minus k. And you will recall that in Matlab, the indices go from 1 to n and not 0 to n minus 1. So in fact, an n-dimensional vector represents a polynomial of degree n minus 1. So consequently, here we have a three-dimensional vector that represents the polynomial we saw above. And so now you can see that the coefficient of the highest power comes first. It's the last coefficient that is the constant coefficient. Now, in Matlab, if a vector is being passed to a function that is expecting a polynomial, the vector is simply interpreted as above. So, for example, if I pass this vector to the function roots, it will simply determine the roots of that polynomial numerically and then print them out. There are some other useful polynomial functions in Matlab, and you're welcome to look them up. One of them is polyder, which calculates the derivative of the polynomial. And so you can see here that this is simply calculated 2 times x plus 3. Polyint integrates the polynomial represented by the vector, and in this case returns a 4-dimensional vector, which is a third x cubed plus 1.5x squared plus 2 times x plus a 0 constant, and you are of course welcome to change that constant to whatever you want. Now, suppose you have this polynomial here, polynomial of degree 4, and you'd like to evaluate this at x equals 2.5. Well, your first idea may be to author some function that calculates x to the n and then call it repeatedly in order to evaluate this polynomial, adding the products of the coefficients and the powers. Well, here's the most expensive way of calculating x to the n. And as you can guess by the name of the function, the runtime is big O of n. So all this function is going to do is multiply x by itself n times. We have a for loop that runs from 1 to n and continuously multiplies the result by x. The only interesting thing here is we have to be careful with negative powers. So the last return calculates x to a negative exponent. And the way we do that is we use the relationship that x to the n is equal to 1 over x raised to the power negative n. However, if n is negative, then negative n becomes positive. However, you have to be careful because int min, the smallest possible integer value, if you actually calculate the absolute value of that or negate it, you get the same value back, the smallest negative number. Try it yourself. You're going to find that it doesn't produce a positive number. It still produces itself. So negative int min is still a negative number. All right. So if you're going to be programming, you have to make sure that your code takes this into account at all times. All right, so here we have two recursive calls, but they're only calling it once, and that's okay. The runtime of this function is big O of n. So this is about as expensive as you can get. So now if we wanted to evaluate a polynomial, we would simply multiply the corresponding coefficient by the corresponding power of x, adding the results together. And as you know from your course in algorithms and data structures, the runtime of this is going to be big O of n squared. Now here's a recursive means of calculating x to the n. For example, x to the 8 is x to the 4 squared. X to the 13 is x to the 6 all squared times x. So we can implement the formula we see on the right recursively. So just to emphasize what's happening here, this calculates x to the n over 2. And if n is odd, then the result is truncated. This simply squares the result. And here, n and 1, bitwise and 1, returns 0 if it's even and 1 if it's odd. So if it's even, we will just return the result which we've already squared. If it's odd, we will return the result which was squared and then multiply it again by x. The balance is dealing with negative powers, and we've already discussed that previously. The runtime of this is now big O ln of n. We can now call this more efficient means of calculating x to the n, and this now gives us an algorithm for evaluating a polynomial that runs in big O of n ln of n time. So almost linear, but not quite. Now, if you're authoring an embedded system, then you really can't use recursive function calls. So another way of calculating x to the n efficiently is to look at the binary representation. So for example, x to the 21 is x to the 16 plus 4 plus 1, which is essentially the binary representation, which is x to the 16, x to the 4, x to the 1. So what we could do is start with x, square it, and continue squaring it, and only adding that power of x if there is an appropriate bit in the binary representation of the exponent. All right, so if you're interested, you can take a look at this code and you will see that it actually does work. So this basically looks at the bits of n and then calculates x to the n based on that. The balance just again deals with negative powers. This is an iterative way. Now, interestingly enough, this is more efficient than the recursive way as we are not making successive function calls. So the runtime of this is still, however, big O of ln of n. And if we use this in our previous function, then we can evaluate a polynomial in n log n time, but at about half the time that it took with the recursive calculation of x to the n. Here, however, is an even more efficient approach to evaluating a polynomial at a point. We're going to get rid of calling an external function to calculate the power. Instead, what we're going to do here is we're going to start with term. Term is initialized to 1.0. Then, with every single iteration of the loop, we will simply multiply this term by x. So with the next iteration, it's x. With the iteration after that, it's x squared, then x cubed, and so on and so forth. We will then calculate our result by multiplying the coefficient by the corresponding term. This is actually very nice because this now requires, if you look very carefully, approximately 3n flops, or floating point operations. So, all right, that's pretty good because that means now that the runtime of this is down to big O of n. So we started with a polynomial evaluation that was n squared, then we went down to one that was n log n, and now we are down to big O of n. Now, all of these approaches are the result of evaluating the polynomial in the standard form. The coefficient of the highest term times that highest term, and so on and so forth. Let's rewrite that polynomial. So, for example, let's take a look at x to the fourth and x to the third. Well, between those two, I could factor out an x to the third, and so now I'm calculating 1.2 times x minus 3.8 and multiplying that entire result by x cubed. Well, having factored out an x cubed from that, let's take the term with x cubed and x squared and factor out an x squared. All right, so now we've factored out an x squared. So given the previous result, we just multiply 1.2x minus 3.8, multiply that by x. Add to that 4.9 and multiply that result by x squared. So let's do that one more time. Let's factor out an x from the first two terms that are left. So we've more or less completely rewritten the polynomial in a form that doesn't at all look familiar. Yes, you could multiply it all out, but again, this is not the form that you would normally consider representing a polynomial as. However, this is actually very efficient for evaluating the polynomial. If you take a look, we multiply 1.2 times x and then perform a subtraction or addition. That's 2 flops. Then we multiply the result by x and add something else, 2 more flops. Multiply by x and add something else, 2 more flops, multiply by x, add another coefficient, 2 more flops. You'll notice that this representation only has 2n floating point operations, not approximately 3n floating point operations. So we've reduced the amount of work by approximately a third. So this way of evaluating polynomials is known as Horner's rule. What's nice about Horner's rule, it's actually more efficient than you'd expect. It actually has only approximately half the runtime of the previous version. So what we're going to start off with is not the smallest or the constant coefficient, but the coefficient of the highest term in the polynomial. And in our representation, that is at index degree. Now, this is going to confuse some of you. We have a for loop, but the halting condition looks a little bit bizarre. We will start with k at degree -1, but look at the condition. While k is less than or equal to degree, we will perform the loop body and then decrement k. You're wondering, why is that condition there? Well, notice that k is an unsigned int. So once k is 0, 0 minus 1 is no longer a negative number, but is now, through underflow, the maximum integer value. So we go from 0 up to 2 to the 32 minus 1. So basically, the appropriate halting condition is to stop if k is no longer less than or equal to the degree. With every single iteration of the loop, we will multiply the previous result by x and add the next coefficient as discussed in the previous slide. The runtime of this is big O of n. Now, for those of you who like extreme optimization, this is about as good as you can get in C++. It's about 1% faster than the previous implementation. Here, instead of using a for loop with an index, we're going to use pointers. So coef is going to be initialized with the address of the highest degree in the array. We will then assign to the result whatever is at that location. What we're going to do is we're going to continually decrement the address coef, and we will continue running the loop body so long as coef is greater than the address of the first entry of the array. Why are we going to do this? Because with each iteration of the loop, we will multiply the result by x, and then, star minus minus coef. So minus minus coef decrements the address by one index in the array, and it returns that new address. Star in front of that dereferences that address, so that says, okay, go to the previous address and return what was there. Now coef has been updated, and we have just accessed that entry. All right, most of you will never care about this, but some of you might find that sort of entertaining. However, in reality, if you require such extreme efficiency, you either really need a lot of comments or just use assembly language. Now, you'd never really implement Horner's rule in Matlab because Matlab is interpreted. So no matter what type of loop you implement, it's going to be painfully slow. Instead, what you want to do is, here we've assigned p, the polynomial x squared plus 3x plus 2. The polyval, polynomial evaluation, takes a polynomial as a first argument and an x value as a second argument and evaluates that polynomial at that point. So evaluating the first polynomial at 0.3 gives 2.99. If the second argument is a vector or an array or a matrix, it simply evaluates the polynomial at each entry of that vector or matrix. Now, important to remember, what Matlab is doing is it is not going to try to do this in Matlab. Instead, someone has written a piece of code in C++, compiled it, and then when you call polyval, it will simply pass pointers to that function so that that function can consequently perform that polynomial evaluation using Horner's rule in compiled C code or compiled Fortran code, depending on how old your version of Matlab is. So polyval will evaluate the polynomial using Horner's rule. Following this topic, you now understand the representation of polynomials that we will be using for C++, but also the representation of polynomials that is used in Matlab. And they are different specifically because Matlab indexes its vectors from 1 to n, whereas arrays in C++ are indexed from 0 to capacity -1. Consequently, there's a more natural representation for each. Now, we've also seen successively more efficient means of evaluating polynomials. So rather than just starting with the most efficient, we went through successively more efficient implementations, seeing various tricks at every single step that may be used elsewhere, and then ultimately ending up with the very efficient Horner's rule. Now, in Matlab, you know now that you can call polyval and that this is going to evaluate the polynomial using Horner's rule. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!